All right, so nobody remembers what I talked about last week? About the oxalic acid, its chemical reactivity? You know, one of the things that I recommend repeatedly is just a review. You know, just review your notes. Like I said, I try to review it every day or close to every day, and it's quick because when you're reviewing notes, it's very easy to read that. And by the time the final comes along, you have everything memorized. Like by the time the final came along when I was at, let's say, at UCLA, you know, I had everything in my notes memorized. I didn't really have to review. You know, I could look through the homeworks or stuff that I didn't have memorized, but there wasn't that much review. But it's so easy to forget. And so the stuff, we were talking about last week is probably long since gone, and the stuff we were talking about last semester is probably long gone, right? Well, I didn't have a lot of you from last semester, but, think about Chem 1A. Did I talk about oxalic acid last week? The icebox? What was I talking about, the icebox? It's a bad reducer. That's the answer I was looking for. It's a bad reducer. Everybody should know it's a bad reducer. Why? Because you expect it to be more of an oxidizer rather than a reducer because of its plus what oxidation state? Oxalic acid. It's +3. What do the oxidation states on carbon range from? They range from plus what to minus what? -4 to +4. That's good. And so +3 is on the what we call the electron poor side. +4 is electron poor. So something like that, CO2 is electron poor, right? And so that should be an oxidizer. And the question is, then why do they use CO2 in fire extinguishers? Because if CO2 is an oxidizer, that's like spraying oxygen on a fire. If you got a fire, would you give the fire O2 gas? No, you'd just be feeding the fire, fanning the flames, they call it, right? And so why is CO2 used as a fire extinguisher? Because it's a very bad oxidizer. It's not going to oxidize anything. The only thing CO2 is capable of oxidizing are the incredibly good reducers, the powerful reducers like what? Yeah, some organics actually organics aren't even powerful enough for CO2 because most of them are carbon. And so when you look at the driving force, there's no driving force. It's for the metals like. Would you use CO2 on a sodium fire or lithium fire? No, you're asking for big trouble. And so CO2 is a very bad oxidizer, which means that oxalic acid should be a worse oxidizer or a better oxidizer? A worse oxidizer. So oxalic acid is a bad oxidizer. And even worse than its oxidizing ability is its reducing ability, because it's not a great reducer because it can only give up one electron and go to CO2, right? And so it's not like it's highly flammable stuff, oxalic acid. It's like vinegar, Is vinegar highly flammable? No, you could try catching your oil and vinegar dressing on fire. It'll burn, right? The oil for sure, but the vinegar part, just get some vinegar and try it. Well, actually, don't try it. But you probably can imagine what's going to happen. Nothing much is going to happen, right? And so the same thing. This is a very bad reducer. And so what we got is a powerful oxidizer and a bad reducer. So should we add the bad reducer or should we add the powerful oxidizer? Which one do we add? Add the dichromate to the oxalic acid or add the oxalic acid to the dichromate? Yes, good. That's common sense says add the dichromate to the oxalic acid. Why? Yeah, you don't want a violent reaction. The reason is, and this is why it's easier to control the reaction, the analogy I used this morning, which isn't so great, is like, think of oxalic acid as piranhas. If you're just adding one piranha at a time into the pool, then it's not going to be so violent. You aren't going to see all the bubbling and all that other stuff. But if you dump in all the piranhas at once, it's going to be violent. Or if you feed whatever you're feeding to the piranhas, and you got thousands of piranhas there, it's going to get violent, right? And so the reason is we always add the reactive species, even though it's not an acid. Here's a violation of the AA, add the acid. No, we better not add the acid. We better add the dichromate. And so this is what I mean by thinking through. You could do the cookbook. The cookbook procedure just says add. But some people in their haste, in their rush, forget, and they just mix them together. It's happened. People just dump it together, and it generates gas. We'll see. And it wasn't an explosion or anything. It was just a violent foaming reaction, just lots of foam, and it splattered. And so they got orange dichromate all over their hands. They weren't wearing gloves. They got it all over the clothes. Do you want dichromate all over your hands and clothes? No, but they did. They got it all. But one way to prevent that is to buy some gloves. You can buy nitrile gloves, Like somebody was telling me over at Walmart, they sell a box of 100 nitrile gloves for $8. It's cheap. Because if you go to Costco, it's like $10 for a box of 100. So. Or you could go to the 99-cent store and buy one pair for 99 cents. But it's a very thick pair. But they have a finite lifetime. So, but I recommend wearing gloves. Actually. Okay. Next, what was I going to say? Oh, speaking of stuff from last week, who solved X? Who solved X? You got stuck. Okay. You got. Would you say stuck and close or stuck and lost in a infinite desert? Stuck and close. All right. All right, then let's do this. I'm going to give you 10 minutes. Why don't you just finish it up? You guys can work together if you want. Will you work with your neighbor or friends or strangers and solve for X? And then we're going to have this as a quiz. So you can just give me your answer. And Anthony, if you have to leave, just write your name down, give it to me, and then take that.